on. So we are discussing this homogeneous catalysis and mainly alpha beta migratory insertion we were discussing. Previously we were discussing the oxidative addition. As you have seen, we have also discussed reductive elimination, opposite of oxidative addition, right? The requirement for oxidative addition and the reductive elimination is just opposite. And we have seen also alpha migratory insertion, where alpha position things are moving, not at the beta position. But also we have seen beta migratory insertion, where we see at the beta position things are moving, alpha beta, alpha beta. This is the alpha beta, alpha position things were moving, right? Of course, there could be a gamma, alpha beta, gamma migratory insertion, but those are little less predominant. We see very rare examples of those. Nothing really industrially relevant. That's why, although scientifically it is feasible, we are not really going to discuss gamma migratory insertion or elimination reactions. Okay, another thing you need to understand, the opposite of this alpha migratory insertion would be alpha elimination. That is, again, we can come back and discuss separately, but just to say you that if you start from here, these metal acyl species, if you are to get the alpha elimination, then this CH3 group will migrate on the metal and you will get the CO process. Just like oxidative addition and reductive eliminations are opposite to each other, alpha migratory insertion and alpha elimination are opposite, just kind of microscopic reversal.
Excuse me, sir. Sorry to disturb you. I'm not able to see the PPT.
Oh, you are not? Krishnam, are you seeing it? Okay, let me share it again. Try to share it again. Can you see it now, the slides? Mamta?
No, sir. I'm not able to see.
Can
Maybe
you
I will
log out?
log out. Yeah, and again I will join it.
Please.
Yeah, I will try this. Sure.
Can you see now?
Yeah, now it's perfect.
Okay. So Krishna, hopefully you are seeing it again. So moving on to what we were discussing, the opposite reactions, both the forward sense as well as the reverse sense reaction, both are really important industrially, pharmaceutically, academically, wherever you want to see it, these reactions are very important. So the forward sense, we have alpha migratory insertion. The reverse would be, reverse of this reaction would be alpha elimination. So you get carbon monoxide back as well as methyl on the metal. So forward is insertion, reverse is elimination. Similarly for beta, beta migratory insertion and beta elimination. These are very important transformations, just like oxidative addition as well as reductive elimination. We have seen these reactions. I'm not getting into more detail. You get acetyl, the aldehyde type of product. You have seen the Monsanto acetic acid process, where you see from the simple material you get acetic acid product. We have briefly discussed the mechanism. Now, of course, in every cases, it would not be possible to do this sort of oxidative addition and reductive elimination, and alpha migratory insertion, beta migratory insertion, and so on. But specifically in cases where you cannot do, let's say you need to do a sequential oxidative addition reductive elimination, that essentially will allow you to exchange the partner, okay? But if it is not possible, then that would allow you still to do this reaction four-centered reactions mechanism. Let me give an example, it becomes a little bit clear. Let's say you have ligand metal, so ligand is L, metal complex. It has a partner, metal has a partner A. You want to exchange this A with one of the partner of XY. This is another reagent. Two different reagents you have, LNMA and XY. Now you want to exchange it. What would be the way to exchange it? As you have seen previously, you can undergo oxidative addition. Okay, this is not oxidative addition. You can insert the metal into it and then reductive elimination to give you this two products. So you see XY was there, X is now replaced by A. You form AY and metal X complex, right? So this starting material and this product formation would require oxidative addition into this XY and then departing or leaving each other. In a way, the partner is exchanged. So this partner of metal is exchanged with X. This is what essentially the oxidative addition plus reductive elimination net result, right? Is it clear that you can change partner on the metal or on the organic molecule by doing oxidative addition and then a reductive elimination? So metal will insert on XY and then the partner will change. So A will go with Y and X will stay with metal. But this sequential oxidative addition and reductive elimination, it may be not possible in every cases. It could be due to the metal is not having sufficient electron density to insert into XY, as we have discussed into the oxidative addition, that metal has to have electron rich ligand or metal has to be electron rich center. If metal is not sufficiently electron rich, you will not be able to oxidatively insert into the XY bond. But in those cases, what happens, still you can get the desired partner exchange if you are giving extra energy to the system. Okay, so that mechanism is called four-center reaction. So you see metal A, X and Y, four different centers, okay, put together. It's just like joining hand and then they change the partner. Okay, they join hand and then they change the partner. M was with A. Okay, at the end of the reaction, M is with X and A and Y together. This part comes out together, give you that M is with X. This is called four-center reaction. As you can see, four centers are involved into this reaction. But these reactions will require higher energy. So to speak, industrially, it is not something very often we will see, but it is there. Whenever oxidative addition and reductive elimination is not possible, but you need the net effect of oxidative addition and reductive elimination, these sort of four-center reactions are looked after or promoted by giving high energy. This high energy could be in the form of high temperature. You heat it really hard, okay, and then you get it. It could be by other method, but pressure, for example, you pressurize it and do the reaction, high pressure reaction, depends. But Oxidative addition and reductive eliminations are relatively easier reaction. The energy barrier for these reactions are relatively less, whereas force-centered reactions is under forceful condition. Okay, what is an example? It is in here, as you can see. It's a zirconium complex, dicyclopentadienyl zirconium alkyl halide complex. So this is the alkyl group. It could be any other alkyl group. It could be halide, like as you see in here, and 2Cp2. Now zirconium is +4 oxidation state here, 1 minus, 1 minus, 1 minus, 1 minus. Total 2 minus, another minus, 3 minus, and 4 minus. This total 4 minus unit is reacting with iodine to give you, as you can see, the partner has changed. Iodine means 2 iodide atoms were there. One of the iodide atom has exchanged the position with this alkyl group. Now everything, dicyclopentadienyl zirconium halide remains, and then this iodide change position with this partner, with this big alkyl moiety, and another iodine atom is attaching with this alkyl partner to give you this alkyl iodide. Right here, the most important point we are trying to draw here is iodine is not oxidatively adding. Zirconium is not having iodide here. Okay, it's a 4 coordination right now, so 6 coordination is not happening. Why it is not happening? Because zirconium is 4 plus. It's a D0 electron system. There is no longer electron available to do the oxidative addition into iodine, and that is why this sort of mechanism that is happening here. I'll explain again. So let's forget zirconium. Let's say this is some other metal. What could have happened if there is electron available on this metal to undergo oxidative addition? Iodine would have undergo oxidative addition. So on this metal, if there was enough electron, then iodide and iodide, this oxidative addition would have gone. So between iodine and iodine, oxidative addition, metal insertion would have happened over here. Okay, so this metal, of course it is not possible, but if a suitable metal was there, oxidative addition into iodine would have been possible. And from there, this one of the iodide and this partner would undergo reductive elimination. Okay, you could have had a iodide here and iodide here. This iodide could have gone with this one to give the alkyl iodide, and the other iodide which was here would give you this compound. So oxidative addition, reductive elimination would have given you these two compound anyway. Is it clear? Let me explain again. So if you have a suitable metal, not zirconium, it would have oxidatively add onto the iodine. That means inserted, it would have insert into the iodine bond. If that happens, let's say in the axial position, one iodide would have come. On this axial position, another iodide would have come. That's the oxidative addition. Iodide here, iodide here. Now the reductive elimination would be between this iodide and this alkyl to give you alkyl iodide, and then remaining is this molecule. Right. So oxidative addition and reductive elimination could have given you these two products. But in this case, oxidative addition and reductive elimination sequence is not possible, because for the oxidative addition your metal has to be electron rich. There should have been some metal electron available. In this case, zirconium is 4 plus, no metal is available, and therefore you would not get any oxidative addition. Okay, so this is where we needed a four-center reaction mechanism. So the four centers are attaching on each other. As you can see by this mechanism over here, you would get the oxidative addition. Okay, so this mechanism is possible only when it is absolutely necessary. I hope it is clear. This is not always the case. This mechanism we will not follow all the time. Only when it is necessary, we'll follow this reaction mechanism. Let me get back to another type of reaction which happens all the time, you may be familiar with, that is ligand substitution reaction. This is another fundamental type of reaction. Once we are done discussing this fundamental type of reaction, we'll then just simply discuss the industrial relevant processes or catalysis by utilizing these fundamental processes. So therefore, hold on with us that it is important to understand the steps. It is important that we understand the fundamental processes. So what is happening here? The ligand metal complexes are there, and associative mechanism, in an associative ligand substitution mechanism, what happens? Ligand metal attaches with another ligand which has lone pair or electrons, right? It attaches it. So ligand metal and A association happens, and one of the ligand goes out. So the overall process could be, first one of the external ligand is coming and joining with metal, and then ligand is going out. That is called associative mechanism. Dissociative mechanism could be the one where before this external ligand comes and joins, one of the ligand is already dissociated and then the external ligand is joining. Let me try to explain one more time. So you have a metal center. As I said, metal center itself is not really going to be always possible to stay itself. You need ligand holding the metal center. Now this ligand can be removed, another one can be brought back in. The mechanism for these reactions could be, one of the existing ligand from the metal center can go out first and then another new one can come in. That is called a dissociative mechanism, where one of the ligand arm from the metal gets to go out and then a new ligand comes in. That's the dissociative mechanism. Associative mechanism, net result is same, but associative mechanism is nothing going out first. First, from outside, extra ligand comes and sits on metal, and then from the metal, one of the older ligand goes out. That way, overall, one ligand exchanges for another ligand. Is it clear? We are discussing how on the metal center one outside ligand or new ligand is exchanging with the old ligand, right? Two mechanism, associative, where everything gets associated first and then one thing goes out. Dissociative, where one of the old ligand first dissociates out of the metal complex and then a new ligand comes in. Okay, so these two mechanisms, we'll come back to these later as well. Now, so you look at this complex, it has 4 hands. This palladium complex has one phosphine ligand, another phosphine ligand, one halide, and this alkynyl partner. What would happen first here? In this case, it could happen that this phosphine ligand first comes out. So there is a vacant site. Nothing is here now. And then this new ligand, new organic molecule or new ligand comes and attaches to it. So that's a ligand exchange. So phosphine goes out, olefin comes in. Ligand substitution. It could have been other process where olefin comes and sits on here and then this one goes out. That is not going to happen in this case. Here one of the ligand goes out first and then olefin comes in. Okay, so this sort of thing we will be seeing again and again. I will remind you when you see it again. Okay, so these sort of ligand exchanges are quite common in the domain of catalysis. In industrial application, many times you would see these things happening. In the organometallic catalysis domain, we call it transmetallation. This is nothing but a ligand exchange as well. Let's say, take an example first. You have a metal complex with palladium. 2 phosphine ligands are there, right? And oxidatively added bromobenzene is there. Benzene ring and palladium inserted into the bromobenzene carbon Br bond. And these 2 phosphine ligands are there. Now you want to exchange this bromide. This is a ligand. So the 4 ligands are there on palladium. What are the 4 ligands? Phosphine ligand, bromide, and benzene. C6H5 minus, right? 4 hands are there for this palladium. What is the palladium oxidation state? Palladium 2 plus, right? 1 minus, 1 minus. Palladium 2 plus, what's the electronic configuration? This is going to be D8 system, right? D8, because palladium was D8S2. 2 electron goes out, palladium 2 plus, right? And this is going to be a D8 system. So it should be a square planar complex. D8 systems are square planar, not tetrahedral, plain molecule. Now these 4 ligands are there. 1, 2, 3, 4. You want to exchange this bromide with this partner, right? This partner, which is the olefinic partner. How would you do that? This bromide will react with, for example, with NBU3SN, butene bromide will be generated, and this olefin from tin reagent, it will transfer onto the palladium. So this process, or this is an example of transmetallation. You see, this the same thing is written here. You have a ligand or many ligand, different ligand, same ligand, doesn't matter, ligand metal X. So all these are ligand Ln, these 3 are ligand Ln, metal X, ligand metal X, ligands metal X, MR. This whole thing is MR. This is R. This whole thing we are abbreviating as metal M with substituent. It could be ligand metal R. So these ligands metal and R group. This R group is transferring onto the palladium on this metal center. You get MX, which is here MX. Okay, MX and R is transferring onto the metal. So the alkynyl is transferring onto the metal. Okay, is it clear? Okay. Now we need to understand few of these things little bit in more detail. Okay, this is when in our very first class what we were discussing, the electron count for the metal complexes will come handy. Okay, let's slowly discuss this. Now let's say you have a iron complex. As you see over here, this is an iron complex. What you have in here, you have iron triphenyl phosphine, also the phosphine ligand, triphenyl phosphine, methyl ligand, CO ligand, and cyclopentadienyl ligand. It's a CP, right? Cyclopentadienyl ligand. So this is 1 minus, this is 1 minus, this is 0 oxidation state, phosphine is neutral, carbon monoxide is neutral. 2 electrons it gives, 2 electron it gives, 2 electron it gives, 2 electron it gives. Iron is 2 plus because this is 1 minus, this is another minus. So 2 different minus, neutral, neutral, right? What is the electron count? Well, as you know, iron is D6S2 system, but iron 2 plus would be D6 system, right? Now these 3 ligands, it is going to give you 6, right? It is going to give you 2, 2, 2, 6 electrons, plus this has 6 from iron 2 plus, 12, Cp minus, which is basically a 6 electron system, so that is going to be give you total 18 electrons, right? Total 18 electron. The electron count for this is going to be total 18. Now if you are reacting with carbon monoxide, so this sort of complex, if you are reacting with carbon monoxide, what happens? That's the question. Okay, this iron Cp MECO triphenyl phosphine complex, it is, if you are adding carbon monoxide to iron, you will get a 20 electron complex, which is not feasible. Anything more than 18 electron complex is difficult or near impossible to generate, or let's say, of course, I mean, you know, very rarely feasible, or that is because you have s orbital, p orbital, and d orbital. So s orbital can hold up to 2 electrons, p orbital can hold 6 electrons, and then d orbital can hold 10 electrons. So total to 10 plus 6 plus 2, 18 electron is feasible. So another extra ligand such as carbon monoxide cannot join with iron. This is the reason why 20 electron, this sort of iron species, is not possible. Of course, these reactions are done under high pressure of carbon monoxide. Lot of carbon monoxide gas is given on this complex, and you are asked what will happen. This complex is out of really contention. Then what happens? First step what happens is, when you take this complex, react it with carbon monoxide under pressure, first thing is you see this alkyl group, R group, it transfers to carbon monoxide. So alpha migratory insertion is happening. Okay, this alpha migratory insertion happens first. So the alpha position of the carbon monoxide, this carbon, this is the alpha position, this is beta position. At alpha position, methyl group is transferring. Now you see what is the electron count. What I said, iron is D6 system, or 6 electrons are there. Iron is 2 plus here as well, 1 minus, another minus. So 6 plus, sorry, 6 electron, 6 electron, 12 electron, plus 2 electron, 14 electron, plus 2 electron for this bond, right? So total it becomes 16 electron. 6, 6, 2, 2, total 16 electron. Now once it is 16 electron, then it can take another carbon monoxide. So the carbon monoxide come into picture. What I was saying, the new carbon monoxide comes in. So this is the new carbon monoxide that is comes in. So what I was trying to tell you that if you take this compound, react with carbon monoxide, another addition of carbon monoxide as it is on to add. So 2 carbon monoxide unit is not going to be feasible. So the total 20 electron species is not feasible, and also the back bonding and other problem also come into picture. But let's say just 2 carbon monoxide addition onto this complex, 1 carbon monoxide is there, another carbon monoxide cannot come in even if you put a lot of pressure of carbon monoxide. Okay, this is the fundamental basis why this dicarbonyl iron species cannot be forming. Now, what will be happening? First thing, although you are reacting with high pressure CO, first thing what will happen that methyl will undergo alpha migratory insertion. This will transfer alpha migratory insertion as you see in here. Then CO, which is now ready because it is 18 electron to 16 electron species now, CO can come back in. CO is another ligand, so it would be back to 18 electron. So a new CO has come in and new acyl group is formed. That would be the product formation from these reactions. Okay, so just to sum up what we told so far, that we will be able to have a reaction where it would require a prior reaction to happen, a background reaction to happen to accommodate carbon monoxide or any other new ligand. So this is what we are seeing over here. Is it clear? Okay. Now let me tell you a case where this is really also little bit difficult to be happening regarding this carbon monoxide reaction. With carbon monoxide, as we were discussing in the last class, although it is very poisonous gas, industry uses it quite a lot, and it is a C1 carbon source, right? That is fantastic source of making new molecules. Okay, what we are seeing over here, that this carbon monoxide on this zirconium Cp2, the same complex we were discussing in the last class, where 2 dicyclopentadienyl zirconium methyl chloride is there. It's a 16 electron complex. Okay, this is a zirconium 4 plus D0 system. Okay, Cp cyclopentadienyl is having 6 electrons, and 2 of them 6 plus 6 12 electrons. This is methyl 2 electrons for this bonding, and chloride 2 electrons for bonding. 2 plus 2 plus 6 plus 6 plus 0 for zirconium. So total 16 electron complex. Now if we are trying to react this 16 electron complex with carbon monoxide, we will get an 18 electron complex immediately. Okay, but the problem here is, as I said, zirconium does not have any electron left on it to backdonate or to stabilize the carbon monoxide. So what happened? Although it is goes to 16 electron to 18 electron, although this should be little bit stable molecule, but it is not, because zirconium cannot stabilize this CO complex. CO addition or CO association, as I said, would require donation from carbon monoxide to metal, as well as metal should be able to give back the back donation into the carbon monoxide. Since zirconium is not having anything to give back to carbon monoxide, this complex is not going to be stable. I repeat, zirconium is 4 plus, no d electron, no electron available on it. The total electron count for this complex simply is 6 plus 6 plus 2 plus 2 plus 0, that is 16 electron. Over here, it reacts with carbon monoxide to give you an 18 electron species. As we discussed before, 18 electron species are more stable. But in this case, it is not. That is because zirconium is 0 electron. So zirconium 4 plus 2 Cp is 6 plus 6, 12 electron. 2 electron 14, 2 electron 16, 2 electron 18, total 18 electron complex. But metal carbonyl species, to be stable, we need to have metal to carbon monoxide back donation. What we have learned previously, that any ligand which can donate to metal will be called as ligand. Any substituent that can donate to metal, that is ligand. But for the carbon monoxide to be stable, ligand has to give back to the metal has to give back to the ligand. So since the metal doesn't have any electron, this complex is not stable. Then what happens? Alpha migratory insertion happens. So this methyl will immediately transfer onto CO. Okay, this methyl immediately transfer back to CO. Can it take another CO? No, it cannot, because it is further electron deficient. Now it has COMe. Previously it was little bit electron rich because this methyl substituent was there. That's why CO, it was possible to come in. Now, of course, zirconium doesn't have an electron. On top of that, COMe is an electron withdrawing group. That means zirconium cannot, although it is 16 electron species, just like here, zirconium cannot take another CO. What it does, it essentially gets stabilized with the lone pair of the oxygen, that you know, oxygen in this case will have 2 lone pair. It donates to zirconium to give a 18 electron species. Okay, so this is 2 electron, 1 lone pair participate. Of course, there is still 1 more lone pair left. This lone pair gives and stabilize this as a 18 electron species. So what we have told so far, that these sort of zirconium complexes, for example, it can be other metal complexes under similar situation, we can have quite exciting behavior. Number one, this is a 16 electron species to start with. It's a D4 system. It can react with CO. But these sort of complexes, characterization will not be feasible. Right? That is because for characterization, these need to be stable. There is no crystal structure so far obtained where a D0 carbon monoxide species is stabilized. That would be really, really wonderful if anybody can show that D0 carbon monoxide species is crystallographically characterized. That's a great research topic. In any case, this species, since it is unstable, immediately undergo reaction where you see alpha migratory insertion is happening. Now, this alpha migratory inserted intermediate cannot undergo further CO addition. That is because this is very, very electron deficient. What it does to gain the 18 electron, why? Because that gives the stability to the complex. This lone pair on the oxygen donates to zirconium to make it an zirconium 18 electron complex over here. Okay, I think that is so far we have discussed. I hope you understood both the previous case and this case. So previous case was an alpha migratory insertion happens and then CO adds. But in this case, alpha migratory insertion of course happens first, then CO cannot add, right? So you see the beauty of these two systems. In this case, of course, CO addition directly was not possible because it was 18 electron, 20 electron was not possible. So the alpha migratory insertion has to happen and then CO addition can happen. In the next case, you see CO, there is no alpha migratory insertion option here because CO is not there to start with. CO addition is possible to make it 18 electron species. Then alpha migratory insertion, just like in the last case, it is possible. But in the last case, you see that CO insertion was feasible after the alpha migratory insertion. But in this case, alpha migratory insertion cannot be followed by CO addition. And that is because this metal is highly electron deficient. So look at these two cases. You will see the versatility of this CO addition depending on the electronic structure and the ligand type of ligand you have. The beauty of these different intermediate or complexes will dictate the product formation. As you can imagine, industrially, these sort of fundamental processes will be key towards planning a synthetic strategy or strategy to prepare organic molecule of importance of pharmaceuticals or agrochemicals, fungicides, pesticides, whatever you want to need it, or materials, you need it, you need to understand the reaction mechanism, how it is going to happen. So these two cases, although they are connected, but they cannot be more different. They are having completely two different scenarios. Okay, I will discuss one more thing before we close today. That is a little bit exciting, at least I am excited about it. And that is a simple question that I think we want to understand whether the migratory insertion, let's say alpha migratory insertion, the R group migrates or CO inserts. Is it clear, the question? The R group, the alkyl group, is it migrating or CO is inserting? Whether I am going to you or you are coming to me. Which is constant? Which is sitting idle, the other guy is moving. So is it similar? Is it sun rotating around earth or earth is rotating around sun? Okay. Now this is a very important and critical question. If R group is migrating, then you will see, let's say R migrating to this axial position, you will get this product and this place will be vacant. Now, if CO is migrating, this CO is migrating over here, then this place becomes vacant and then you get COR. If you do this reaction under excess CO, this vacant position will be taken up by carbon monoxide. Right. Now, I think it's very difficult to design an experiment which would be able to tell us whether R is migrating or CO is inserting or CO is moving. Which is moving? R is moving or CO is moving? R would be migration, CO would be insertion. If CO moves, that would be insertion, it is inserting. R is migrating either on carbon or oxygen, or of course in carbon, to the carbon monoxide. Now, which is happening? How one can prove that? This is, I would say, very difficult experiment scientifically to be done, but scientist has designed, I think design has to be perfected. What they have done, they have taken a manganese pentacarbonyl complex with a methyl adduct. This manganese carbonyl, one of the axial carbonyl, is labeled, as you see in red. It is labeled with labeled carbon, like let's say 13CO. Right? Rest of the carbonyl are not labeled. So it is possible to have an axial CO labeled, one of the CO labeled methyl manganese pentacarbonyl complex. Now you are hitting, let's say, in presence of normal CO. So two different type of CO are there. One CO is leveled CO, 13 carbon. This is 12 carbon, normal carbon monoxide, normal carbon monoxide, normal carbon monoxide. This is leveled carbon monoxide, right? Now, what are we looking at? CO, if it is, as I said, doesn't matter whether R moves or CO moves, the vacant position, since it is done under CO, new CO will come in, which is not leveled CO. What is happening here is, if CO migrates, okay, if CO migrates, what will happen? Or if CO inserts, migrates means CO will be inserting, what will happen? If methyl is migrating, what will happen? If methyl is migrating, methyl can migrate where? In the ortho position, means nearby position. So this is 60 degree or 90 degree, right? 90 degree. So this can go in here, methyl can go in there, methyl can go in there, methyl can go in there. So all the methyl cannot go on the trans position. This is trans, right? That is because 180 degree and it is opposite to each other. This sort of transfer is not really feasible. Only neighboring group that is at 90 degree angle can be possible. Or migration is happening from here to there, here to there, here to there, or here to there. This you need to focus. Now what we are then getting, if methyl is moving from here to there, you will get this compound, and the vacant position of methyl will be filled by CO, because you are doing the reaction under CO. Okay, so this COMe will be trans with respect to the leveled carbon monoxide. This is 13CO trans. You can characterize this complex. If methyl moves to this position or that position, you will essentially get one of these complex, because both of those complex will be exactly same. The vacant position of methyl will be taken by CO. So if methyl transfer over there or over there, you will get this complex in the middle, and the vacant position which is created due to the methyl migration will be taken up by the CO. Two equivalent it is possible, because it can come over here or it can come over there. So these two positions will give you two equivalent of this. And if methyl is transferring over there, that's only one position, one equivalent of this could be forming. This COMe and this COMe is different, because opposite to this COMe only unleveled CO is there, but opposite to this COMe leveled CO is there. So these two complexes are different. Clear? Now other position could be this methyl is migrating on this CO, right? So that's how you get this compound in another equivalent. So if methyl is migrating, you are going to get 1:2:1 ratio of these complexes. Three different complex formations in 1:2:1 ratio. It is feasible. These are like statistical factors, right? That's because to this methyl, all these methyl carbon monoxides are same, this, and this. So statistically it can go there, 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 or there. Only difference is this is leveled, but this methyl doesn't care whether it is leveled or not. So these are equal probable center for transfer. So this methyl can transfer here or here. It's exactly same, because the vacant position that will be created by methyl upon migration will be taken up by CO. Methyl can come to here, that's a new complex. Methyl can come to here, axial position, that's a new complex. Right. other possibility is, so this is happens if it is migrating. We are trying to answer whether this is happening or that is happening. Which one is happening, this one or that one? Okay. Now, if CO is inserting into the manganese methyl bond, so this CO can insert, this CO can insert, this CO can insert, all of these three can give the same product because the vacant position will be taken up by the next CO, right? Of course, this CO can also insert. So 1, 2, 3 and 4. These 4 CO can insert over here. This CO cannot insert because this is trans to the methyl. Right? It has to be maximum 90 degree to have this transfer. Now, so if these 3 COs are inserting, it would give you exactly this complex, no matter which CO, this CO, that CO or that CO, it gives you this complex. So this is 3 equivalent of that going to be generated. But if this CO is inserting, okay, then you will get a COMe. This is drawn incorrectly here. COMe in the equatorial position, okay, trans to the other CO. Okay, it can be same as is drawn, but it is 1:3:0 ratio, right? And opposite to this labeled CO, if CO insertion is happening, you will never get this complex. Okay, what I'm asking you to look back at this slide and try to see if you can justify this formation. In the next class, I will discuss again. Okay, so if methyl is migrating, what is the case? If CO is inserting, what is the case? We'll discuss from here in the next class. Of course, it is going little bit fundamental, but this is interesting question to answer to understand the fundamental things. We'll be done with the fundamental classes in in 1 or 2 more classes, and then we will be mainly seeing the application. Okay, so today that's what we have discussed. We'll stop it here. We'll see you again tomorrow. Thank you very much. Hello.
Sir, recording has not stopped yet.
Yeah, I am just stop recording.